Is he sleeping somewhere?
No, he was sick. He didn't make it to class this morning, but
Okay.
he's helping his mom, I guess, do something.
Okay. All right, so I did send out an email last night. It was kind of late notice. And I said that I would offer a bonus. So please take out a sheet if you want to have an opportunity at the bonus. Take out a sheet of paper, put your name on it. You're going to turn it in to me. And do not copy off of your neighbors. Okay, because all I want is a simple answer for this. I don't want people cheating on the last day of class. All right, and then I have to fail you because you wanted to cheat on a little bonus thing. It's not worth it, okay? You either watched the video or you didn't. So today is about Maclaurin series, or Taylor series and Maclaurin series. And we come up with this really, really, really nice formula to be able to identify what all the constants in front, well, what the constants in front of this little polynomial in x will be. And the way that you come up with this formula required that you did, that I did what? So I just want you, like, in just words, explain to me how I came up with, like, the C sub 0. I don't want you to do it. I don't want you to calculate anything. Just in words, explain to me what I did. Like, did I blow on it? Like, what did I do? Like, what did I do? Like, did I say, please tell me what? I mean, like, I did something, right? And so just summarize, if you can, in words.
Would it be easier if we could expand it and calculate it? Could we just do that instead of using words?
No, because I'm only going to give you about another 15 seconds.
Okay. What's the question again?
What did I do to get each of the C sub zeros? I'll give you a hint. It was repetitious, what I was doing each time. And then turn it in when you're done. Fifteen seconds. Yeah, that's all I want. I think that's sufficient time. Anyone else?
Do we have to write anything specific on it or just our name?
Just your name. Anybody else? Last call? Last call? That's it? Okay. So what did I do? What did I do?
Again and again and again.
Repetition of the derivative, right?
Yep.
So it works out, if you go check your email if you didn't see this. I don't want to invest the 20 or so minutes it would take for me to show you where this formula comes from. But it's really nice where it comes from. And so all we're going to do today is use it, all right? But if you're one of those people who like to know where things come from, just watch the video. Okay, so let's do this. There was something else I wanted to say. Oh, last class I ended right in the middle of a problem, and I wasn't able to finish it. That's number 20 from the homework for 8.6. My homework video solutions include number 20, worked out from beginning to end. So I would just encourage you to go watch that if you want to see how that problem got finished up, okay? So we have the formula there. I'm going to put it on the side here because I'm going to use it all day. And the formula for the C sub n's is equal to this. And I didn't mention this, but what does this mean?
The nth derivative.
The nth derivative. The nth derivative. We put it in parentheses instead of writing this, because this would mean f raised to the nth power. So to distinguish the two, we put it in parentheses so everyone knows I'm talking about derivative. All right. So if you have a function, if it can be represented as a power series, the goal is to try and represent it and come up with all those constants. And this wonderful formula will give us the constants. What it's going to require, though, is that we can repeatedly take the derivative of the function and hopefully be able to determine what those constants are. Best way to see this thing in action is to actually do a problem, right? To actually apply it to an example. So I'm going to start with the example f of x is equal to sine x. And I want you to do this about a equals 0. Yes, this is 8.7. Now, this section is called Taylor and Maclaurin series. And up on the board a second ago, I said that this was called the Taylor series or Taylor expansion of the function f about a, right? About a. If a is 0, it's called a Maclaurin series. If a is not 0, it's called a Taylor series. So a Maclaurin series is a specific case of a Taylor series. It's when the a is 0. So all Maclaurin series will look like this. So Maclaurin will look like this. Sum n equals 0 to infinity, c sub n. But instead of x minus a to the n, I can just write what? X to the n, because the a is 0. And further, when I'm trying to find those c sub n's, I'll do nth derivative, but I'll be plugging what into the derivative? 0 over n factorial. So Maclaurin is a specific example of Taylor. So I could have said in this problem to start off, I could have said find the Maclaurin series for sine x, right? If I would have said find the Maclaurin series for sine x, it would have been understood that a is 0. Does everyone see how this formula is that formula? Yes? Okay. Now, let's do it. So here's the standard way that I approach it. The book does this also. What I'm going to do is I'm going to start taking a look at the different derivatives of the function, because my c sub n's have something to do with those derivatives. So what is the 0th derivative mean? That means don't take the derivative, right? So this is just going to be sine x. Now what I'm going to do is I'm going to take that, and I'm going to take that 0th derivative, and I'm going to plug in the a, which for us is 0. So let's plug 0 in. What do you get when you plug 0 into this?
0.
Sine of 0 is 0, right? Now I'm going to take the first derivative. The first derivative of sine x is cosine x. And when I plug 0 into that, I get cosine of 0 is 1, right? Then I take the second derivative. And so what you start to ask yourself is, when are you going to stop taking derivatives? And the answer is as soon as you are able to identify a pattern. You need to find a pattern in these numbers. If we can find a pattern, then we'll be able to come up with a formula for it. All right? So what happens when I plug 0 into the second derivative? I get 0. Now the third derivative. What's the third derivative going to be? Negative cosine x. And when you plug 0 into that, what do you get? Negative 1. So far, we started out, we had 0, then 1, then 0, then negative 1. Let's see what comes next. Fourth derivative is what? Sine x. And we're back at the beginning, aren't we? We're back at the beginning, and sine of 0 is going to be 0. So we actually have come back to where we were. So we know what the rest are going to be, right? The next one will be cosine, then negative sine, then negative cosine, then sine. So whatever I have here, this should start repeating itself, shouldn't it? So if I continue this pattern, the next one would have been what? 1, then 0, then negative 1, then 0, right? Okay? So now at this point, keeping all this in mind, that the 0th derivative at 0 was 0. The next one was 1, 0, negative 1, 0, and then that pattern. I'm only putting it over here because I need to erase all this. What I'm going to do now is I'm going to rewrite the sine function. F of x is sine x, is rewritten in its Maclaurin series. Sum n equals, sorry. Yeah, let me write it down. I should be able to write it like that, right? There should be a Maclaurin series for this, which should be c sub 0 x to the 0 plus c sub 1 x to the 1 plus c sub 2 x to the 2, so on and so forth. Right, that's what that sum means. And so I just needed to know what the c sub 0 was, c sub 1, c sub 2, and that's where we go to the formula right here. Right? So let's talk about what this c sub 0 would be for us. And I think for this one, I'll write it down so we see it. C sub 0 should be, according to that formula over there, should be the 0th derivative at 0 over what? 0 factorial, right? So do you know what the 0th derivative is at 0? What is it?
No derivative.
It's 0, right? It's this. So this should be 0 over 0 factorial. What's 0 factorial? 1, right? So this is just 0. So when I come to write this down, I'm going to write it down. I'm not going to clean it up yet. Just want everyone to see what's happening. Are you all clear where that 0 right there on top came from? Right? That it was this piece right here? Okay. Now we move on to the next one, c sub 1 plus. So c sub 1 would be the first derivative at 0 over 1 factorial. So what's the first derivative at 0? It was this number, wasn't it? So 1 over 1 factorial. X to the what power?
First power.
First power. Now I'm moving on to this one. What's c sub 2? Do I need to keep writing it down, or is it okay if I just point to it? Is that all right if I point? So c sub 2 should be the second derivative evaluated at 2, which was, evaluated at 0, which was 0, wasn't it? Over what? 2 factorial x to the second power. What's the next one? Negative 1 over 3 factorial x to the third. And that's where we said the pattern is going to start to continue, right? It's going to start repeating itself. So my next one should be 0 over 4 factorial x to the fourth. then, Ron, welcome anywhere you like. I didn't bring a pillow today for you. It's okay. There's chocolate, though. Plus, what's next? So 1 now. So we're back to this, aren't we? So 1 over 5 factorial x to the 5th. Keep it going. How far do you want to go? 0 over 6 factorial x to the 6th. What's the next number? -1 over 7 factorial x to the 7th. Should I keep going? Is that okay? That's okay. You're going to go out as far as you need to go out to see the pattern, because the next step is you must write this in sigma notation. You have to come up with a formula for this, all right? All right. We comfortable with that so far? All right, I'm going to get rid of everything that has a 0 in it. I didn't have to write them to begin with, but I was doing it to try and help you out since this is our first example. I just wanted you to see where everything was coming from. Those are all gone, right? And so if I just write this out, I have 1 over 1 factorial x to the first power minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. Do you all agree with that? Yeah? Plus dot, dot, dot. Now let's generate the formula for this, like the actual summation. And I'm going to use sum n equals 0 to infinity. What do we notice about all of these things? It's alternating, right? So how are you going to create an alternating series starting with a positive if n starts at 0? -1 to the how about just n? What's n? What's a -1 to the 0? -1 to the 0 is 1, right? Which would be a positive. Then -1 to the 1 would be negative, and then positive. Now you could have used n plus 2, but you get the same effect. Look, if you do n plus 2, just so you know, this is the same as -1 to the n times -1 squared, isn't it? Same base, add the exponents. But what's -1 squared? 1, so who cares? That's the same thing, right? They're the same thing. All right. All right, good. We got the alternating part down. Now what? We have 1 over something. Good. And each of these are factorials, aren't they? Notice I kept the factorial there, like I didn't turn that into a 1. I kept it there intentionally to help us see the pattern. If you start simplifying stuff too early, you'll lose the pattern in there. Okay, I have a 1 factorial, 3 factorial, 5 factorial, 7 factorial. Those are all odd numbers. So you need to create a list of odd numbers starting with 1 and do the factorial of those. But n is starting at 0. So 1 over 2n plus 1 factorial. Remember 2n plus 1 created the odds, right? But our n is starting at 0. So we need to make sure that when we plug 0 in, we get 1, right? And then when we plug 1 in, we would get 3. Plug 2 in, we would get 5. Yes? So that takes care of that part. The only thing left is the x to the powers. But aren't the powers the same numbers as the factorials? So I need to create 1, 3, 5, 7. So x to the what? 2n plus 1. Now, did everyone get a copy of this I handed out? They're laying around on the tables. Everyone see that? Are there any extras? There's one extra here. Oh, there's a couple extras here. Okay, so I printed this out. I stole this from someone. I found it online. But since it's academic purposes, there's no copyright infringement or anything like that because it's just for educational purposes. This is a table of common Taylor series. Now, this is correct for this to say Taylor series. But in fact, every single one of these series given in this sheet are actually Maclaurin series because they're all about A equals 0. So you could just scratch off Taylor up there and write Maclaurin if you wanted to. But it's not incorrect to say Taylor. Look down at sine x. Do you see that we have exactly the same thing? Look at this right here. Right? This was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And do you see that they rewrite it as a sum? They have one sum that starts at 1 and the other one starts at 0. I got the one that starts at 0, right? See? That's it. That is the Maclaurin series for sine. Now it also gives on this table, on the side, it says x is an element of R. This is your radius of convergence. This is saying that the radius of convergence is infinity, meaning that if you did a ratio test on this, right? You remember the ratio test? If I said, hey, take the ratio test on there, you would get an infinite radius of convergence, which means that this is what sine x is. For any x value, doesn't matter what it is, this is the definition of sine. Or if you like, this is sine. But it goes forever. And I told you this when we first started this chapter. What we want to do is figure out how is our calculator determining what sine of 2 is. This is what it's doing. It's plugging 2 into this, and it goes out as far as it needs to go. Right? And I have on the board over here, do you remember me graphing sine and then asking you whether or not approximating it with that line was good? Do y'all remember me asking you this? And then saying, y'all say, no, that doesn't look like sine. But I said, okay, let me try x. Can we kill the lights just real quick, just so you can see this? That's good. Do you remember me saying, okay, how about x minus x cubed over 6? Is that better? And everyone said that looked a little better. Do you see that x minus x cubed over 6 is the first two terms of the Maclaurin series? That's x. 3 factorial is 6. So x cubed over 6. Just the first two terms gives us that black cubic polynomial. But if I keep adding more terms, there, that's the first 3 terms in here. It's better, and then I can just keep going and keep going and keep going. And I can go out as far as I want, and I will actually turn into the sine function. Understand? Does that make more sense now than it did before? I don't know if it makes more sense now. And then I also told you at the beginning of class, notice that all of the powers on the sine function are what kind of numbers? Odd numbers. And we talked about the sine function as an odd function. And that's why, because if you look at its Maclaurin series, all the powers of x are odd. And guess what? If you were asked to do the Maclaurin series for cosine, all the powers are going to be even because cosine is an even function. And your Maclaurin series for cosine is on here also. Now, the Maclaurin series for cosine is a homework problem, all right? But I'm not going to get into it right now. Yes?
Is it going to be like this determines the series? Right, the pattern?
There's going to, on the final, there would be 2 types of questions. One question would be, find the Maclaurin series for this function. The other questions will be, use the table to find something else. You got to be careful, because if I ask you a problem like this on the test, and you look at this sheet, because I'm going to let you have this on the test. If you look at this sheet and just write down this sum, and that's all you put, oops, and that's all you put, then you haven't done what I've asked you to do. I want you to recognize a pattern and actually be able to generate this yourself. Am I answering your question? Okay. All right, so everyone sees what cosine is, the Maclaurin series for cosine? Everyone see that on here? I'm not going to go through that, but we all see it's there? Okay. Does everyone see the Maclaurin series for e to the x? Y'all see that? Okay, I'm actually going to do the e to the x one, because I want to show y'all something. Let's do Maclaurin series. Oh, can we get the lights back on? Are they not all? Please. Find Maclaurin series for f of x is e to the x. This one's going to go quick, real quick. So what did I do before? Start taking derivatives, and then I'm going to plug something into those derivatives. What am I going to plug into those derivatives? 0, because it's a Maclaurin series, right? So I'm going to take the 0th derivative of e to the x. What's the 0th derivative of e to the x? E to the x itself. Come over here, take that 0th derivative. I plug 0 in. What's e to the 0? 1. But guess what? What's the first derivative of e to the x? It's e to the x again. And so when I plug in 0 to that again, I get 1, don't I? And it's going to keep happening forever. Agreed? So I'm just going to keep getting 1s. So remember that c sub n is equal to the nth derivative of the function at 0 over n factorial. Because these are never changing, can't I just replace this right here with 1? Like no matter what n is, this is always 1, isn't it? So can't I just say that this formula is 1 over n factorial?
What did we just make 1?
Pardon?
What did we just make 1?
This is 1.
What about the bottom?
The bottom is always part of the formula. You're always going to have n factorial in the c sub n. So when we make this table over here, all we're getting is the numerator. The denominator will always be n factorial. And that comes from the video. If you watch the video, that's the n factorial came out from when we were taking derivative over and over. We kept on getting more and more numbers out in front. So on this one, I actually don't need to write them all out like I did with sine just a second ago. I can go straight to the sum. I know that this e to the x should be able to be written sum n equals 0 to infinity c sub n x to the n, right? That's what it should be able to be written as. It's Maclaurin series, right? But I know what c sub n is. It's 1 over n factorial. So this is just sum n equals 0 to infinity 1 over n factorial times x to the n, which sometimes they'll put it together as one fraction like this. It's the same thing, but let's see, what does your sheet have? It has this one, but it's that, right? Now, if you wanted to write this out, this is 1 plus x over 2 plus x squared. Hold on. 1, 2, x squared over 2. Where am I missing? X over 1 factorial, x squared. Oops. Cubed over 3 factorial. 2 factorial is 2, right? This is x to the 0 over 0 factorial. X to the 1 over 1 factorial. X to the 2 over 2 factorial. X to the 3 over 3 factorial. Forever. We good? Okay. So if you were now to break out your calculator and you say, hey, calculator, what's e squared? Type it in, it's going to give you an answer. What your calculator is really doing is this. 1 plus what? 2 plus 2 squared 4 over 2 factorial plus 2 cubed 8 over 3 factorial plus what? 16 over 4 factorial. And it's doing that until a certain point, and then it's stopping and it's spitting that answer out. Got it? But we can also take something like this now. Find the integral of e to the negative x squared dx. So if we were asked to integrate this, and I won't ask Mathematica or Wolfram Alpha to do it because they will freak out when I do this because you won't be able to do it, all right? I showed you that last class. There were certain things we had run into some weird functions we had never seen before. But according to what we just learned, okay, with the Maclaurin series, I can rewrite e to the negative x squared as what? So look at what did we just say e to the x was? E to the x is sum n equals 0 to infinity of x to the n over n factorial, right? That's what we said it was? Yeah? So replace x with negative x squared into that formula right there. And this would become sum n equals 0 to infinity of negative x squared to the n over n factorial. Do you see what I just did? I used the Maclaurin series for e to the x to rewrite e to the negative x squared as this. Yes? Now, we could try and integrate that right now. We could clean it up. But I'm going to do it a little different. I just want you to tell me if I started expanding that series out inside. I still have not integrated. If I start expanding that, let n be 0, tell me what you would get. Get 1, right, first? Now let n be 1, and what would you get? Negative x squared over 1, right? Negative x squared over 1. Now let n be 2, and what would you get? What would happen if you take negative x squared and square it? But you're squaring the negative also. So positive x to the 4th over, where are we at? We're at 2, right? Over 2 factorial. So positive x to the 4th over 2 factorial. The next one, now I'm letting n be 3. So what are we going to get here? Is it going to be positive or negative? Negative, and then x to the 6th. So minus x to the 6th over 3 factorial. We'll do one more. Plus, it'll be plus this time, right? X to the 8th over 4 factorial. And the next one would be minus, but I'm going to say plus dot, dot, dot. Yes? And now we could integrate that, couldn't we? These are just numbers. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. And so if you were asked to integrate just these things, right? 1, 2, 3, 4, 5. If I asked you to integrate those, why, you'd be in my Cal 1 class, because we just did that in my Cal 1 class, right? That's easy to do. So the answer would be x minus a third x cubed plus a tenth x to the fifth minus 1/42 x to the seventh. Just using power rule. And I could keep doing this, right? Plus a constant. And is this acceptable as an antiderivative of this? Well, as long as you're okay with the fact that it goes forever, and that if you ever need me to actually approximate it, that, you know, how far I go out is going to, again, depend on you and the need, how close I need to be. Questions on this? Y'all get this? Yes.
Is it going to be the same as the series where, like, if we're trying to find a certain window of integration, using the Maclaurin series, we just shift over the domain?
We wouldn't need to shift, and the reason, not for this one, the reason we would not need to shift the domain on this particular problem is because if you look at the Maclaurin series for e to the x, what's the radius of convergence? When it said x is an element of R, that means the whole number line, right? So that means that you would never have to worry about shifting this one over. If you go out far enough, you are going to be approximating that as closely as you ever need to. I don't know if that's what you were asking.
I'm just thinking, like, maybe you'd be able to approximate less terms.
Oh, yes, that, yes. If you were trying to figure out something
That's
like
like
way far out,
So instead of having to go from the center out, you could, like, just get, like, a couple terms for that section.
yes, what Ron is saying is this. Take a look at this picture. In the beginning of this expansion, I'm going back to sine. I think we all agree that in the beginning, my approximation was very close to what sine was doing in the middle, like at near zero. But towards the edges, I'm not very close. In order to get close on the edges, I have to go further and further out, right? I have to add more and more. What Ron's saying is, if we shift over the graph, then we can get closer to the value faster because we don't have to wait for it to go out. That is correct. But I'm not going to ask you to do that. That would be a Taylor series. That's where A is not 0. And that's how we do it. We just shift it. Okay, so with these three things that I've shown you so far, I've shown you actually mechanically how to find the Maclaurin series for sine, right? I've shown you that cosine does have a Maclaurin series, and I've shown you how to get the Maclaurin series for e to the x, right? I want to show you now something, this exciting stuff. I don't know if any of you have ever seen this before. Has anyone ever seen that before? Yeah? What do you know about this equation?
It's beautiful.
It's beautiful. It is. It's argued to be the most beautiful equation in mathematics. Argued to be. I'm not saying it is. It's subjective. But a lot of people say that that is the most beautiful equation in math. I like it. It's good. It's good stuff. But it's only good because we need to understand why it would be good. And just a little background on this. I'm going to actually show you why this is true. And we're going to use Maclaurin series to show it. All right? But first, let me just tell you why we would say this is really nice. There are very important numbers within mathematics that appear many times, and they all appear in this equation, most of the good ones. Like, we know pi has always been pretty cool, right? Like, we like pi. It's the circumference of a circle divided by its diameter, right? And it's just cool, like, irrational number. Now e is really nice because e is the base of the exponential function that when you take the derivative of this exponential function, its derivative is itself. And it's the only function that behaves that way. So e is really, really special. I is the imaginary number, which everybody writes off as being like a joke because Well, it's imaginary, like my friend on my shoulder here, right? I mean, people think you're crazy, but this is very important in mathematics, all right? And then the other two numbers that people don't think are as important are 1 and 0. And those are big time numbers because in our number system, the number 1 is called the multiplicative identity. It's the number that you multiply anything times that and you get back the original number. So like if I take x times 1, I get x, right? So that'll work for every x except 0. And in order for our number system to be called a field, you have to have a multiplicative identity for that to happen. And 1 is it. And then 0 is called the additive identity, and it works almost like that, but it's with addition instead of multiplication. And in order, again, to be a field, you have to have some number inside of the system that acts as an identity over the addition operation. So 0 is the 1. All right? Bring all these nice numbers together into one equation. Now, let's show it's true. All right? You ready? Hold on. Yeah, that's right. Okay. Here we go. I'd like for you to tell me what this is by writing it out, or let's go e to the ix. Let's do that. I forgot to put the x, sorry. E to the ix. I'd like for you to write that out in its Maclaurin series. So what would it be written in its Maclaurin series? So 1, remember I'm using this formula. E to the x is equal to sum n equals 0 to infinity x to the n over n factorial, right? Except instead of plugging in x, I'm plugging in what? Ix. So this is Ix, which means this is Ix to the n, right? So let's start off, plug in 0, what do you get? Plug in 0, anything to 0 is 1, right? Then 0, so the first one is 1. Okay, next. Plug in 1, and what do you get? Ix over 1 factorial. I'll put the factorial there, just so you can have it. What would the next one be? Okay, let's talk about that. Ix squared, right? Over 2 factorial. That's what we would have. Does anybody know what I squared is? -1. Okay, so you have to go back and you have to have seen this at some point in time. I is defined to be the square root of 1. That's what the imaginary unit is defined to be. Square root of 1 is I. So if I square both sides, I get -1. So when I square this, I'm going to get -1 and then x squared, right? Over 2 factorial. Can I write that as negative x squared over 2 factorial? Is that okay? What would the next one be? Ix cubed over what? Over 3 factorial. Tell me if this is right. I cubed, x cubed over 3 factorial. That okay? Is I cubed the same as I squared times I? Is that the same? What's I squared? -1? So could I write the next one up there to be negative ix cubed? Could I? Negative ix cubed over 3 factorial. What about the next one? I plug in 4 now, right? This is all like scratch work I'm doing right here, right? I'm just putting my answers up there. Next one would be ix to the 4th over 4 factorial. Yeah? That would be positive, right? But what's I to the fourth? We got to make sure we're comfortable with what I to the fourth is. It's I squared times I squared, isn't it? Which will be -1 times -1, which will be +1. Yes? And then we have x to the fourth, and then over 4 factorial, so I've got plus, right? Plus x to the fourth over 4 factorial. And I continue through this, right? The next one I'm going to get, anyone have a guess as to what the next thing is going to be? Is it negative or positive? What do you? Positive? Okay, let's do it. Ix to the fifth over 5 factorial is same as I to the fourth times I times x to the fifth over 5 factorial. I to the fourth is 1 times I is I. So you have a positive still. So you're at positive I x to the fifth over 5 factorial. Now the next one will be negative. Won't it? This is the last one I'm going to do. Ix over 6 factorial equals I squared times I squared times I squared times x to the 6th over 6 factorial. You agreed? These two are 1, but I squared is -1. So this gives me negative x to the 6th over 6 factorial. Okay. And it keeps going, right? What do you think the next one would be? I'm not going to do it, I promise. Negative I x to the 7th over 7 factorial. And then the one after that, positive x to the 8th over 8 factorial. The next one will be positive I x to the 9th over 9 factorial. Okay, I think you're with me. All right, that's good? Where is it? There it is. Focus all your attention on the blue. What is that? All even powers. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. That's what? Cosine x, isn't it? The blue is cosine x. So watch what I'm going to write here. E to the ix is equal to the blue part, which is just cosine x. That's not the same blue. Where'd it go? All right. That's okay. Now I need a different color, red. I want you to look at the reds. And for all of these reds, I want you to factor an I out of each of them. Just take an I out of each one. They each have an I, right? Just a single I in it. If you took the I out, what would x minus x cubed over 3 factorial plus x to the 5th over 5 factorial be? Sine x, right, off of that. But there's an I in front of it. Yes? So this would be plus, now the other blue, what the hell? I sine x. Has anyone ever seen that formula before?
Not with the eye.
You haven't seen this before?
Not with the eye.
It's called Euler's formula. I know it looks like Euler, but it's Euler. No? Y'all haven't seen that pre-cal? Pre-cal? No? You never did, no, never mind. I guess if you haven't seen it, you haven't seen it. All right, there it is. That's called Euler's formula. Awesome formula, all right? because this is what's going to get us to the answer. You ready? That was just the setup. Now, I was trying to show you that e to the I pi plus 1 was 0, right? Which if I move the 1 to the other side, I'm really just trying to show you that that's equal to negative 1. Okay, come over here and replace x with pi. And this is cosine pi plus I sine pi. What is sine of pi? Don't fail me now. We've come this far. What's sine pi? 0. What's cosine of pi? Negative 1, which is this. Do you see that? So that means e to the I pi equals negative 1, which means that e to the I pi plus 1 is 0. All right. What the heck? Sorry, my phone's like text after text here. Turn it off. All right, that was bonus material. I don't, that's not in the book. All right. Now, look at this. I want to show you this. You like to give your problems, your problems, friends. You like to give your friends problems. I'm sure when you're out and you're hanging out, you like to do math. But I'll never forget this. This is a problem that we like to give people to really see if they know what's up. What's I raised to the I? So what's I to the I? Right? Okay, so first of all, let me go back to Euler's formula. All right, let me show you something. This is cosine x plus sine, oh, I forgot the I there. This is Euler's formula, right? That's Euler's formula. Can you just get this right side to be I, just by itself? What would you have to plug in for x to give me I here, and just I on this side? Pi over 2? Everyone agree with that? I plug pi over 2 in, sine of pi over 2 is 1, cosine of pi over 2 is 0. So that means e to the I times pi over 2 is equal to I. I know that looks weird, but that's what it means. E to the I times pi over 2 is equal to I. So come back over here. That I right there, I would like for you to replace it with e to the I times pi over 2. And then I'd like for you to raise it to the I. And what do you do when you take something to a power and to another power? You multiply the powers. So isn't this e to the I squared times pi over 2? I squared. What's I squared? Negative 1. So this is equal to e to the negative pi over 2. So I raised to the I is e to the negative pi over 2. That's what it is. It's kind of weird that you take an imaginary number and you raise it to an imaginary number and you get a real number. Right? That's a real number? This is an imaginary to an imaginary. All right. All right, we're halfway done today. Let's, yes?
If we follow you after class, will you explain why there's imaginary numbers?
I don't know. It's a long conversation. I think what you should do if you want to ask someone why they're imaginary numbers is perhaps ask why there can't be. Because just because you can't see it doesn't mean it doesn't exist. I mean, you know what I'm saying? That's right. Or another quote I like. Another quote I like. We may have talked about this. The irrationality of a thing is no argument against its existence, rather a condition of it. That's another way of saying it. It's just weird because it is weird, and that's just the way it is. But yeah, we can talk imaginary numbers, but not here. We got to move on because we've only talked about Maclaurin series. We haven't done a Taylor series yet. So Taylor series, we need to do something for when A is something other than 0. So how about we do find the Taylor series for f of x equals natural log of x about x is equal to let's do 1. No, well, I'm just trying to see. No, 1's going to be too easy. Trying to prepare you for homework type thing. There we go. All right, what's the difference between the Taylor series and the Maclaurin series? So A is not 0, A is 2 in this case. So that means the formula we're using over here, when we did that C sub n, we're trying to find that nth derivative at A, that's no longer 0. In this problem, that's going to be, in this problem right here, it's going to be 2. So just remember that. Now, as far as doing the derivatives and trying to find a pattern, that's all the same. Okay, now the derivatives here are going to be much more complicated than the ones that we had before. So please let me know if you have any issues. Zeroth derivative? Don't even touch it, right? Zeroth derivative, you don't take a derivative. Right. Is it okay if I just draw an arrow over here and just, we all understand that this means I'm going to do the zeroth derivative with 2 plugged in right now? Without me writing this over and over and over? Is it all right if everyone understands I'm plugging 2 into that? What is it going to be here? ln2. All right, now the first derivative. Hey, what's the derivative of natural log x? 1 over x. What happens when I plug 2 into that? 1/2. It's not so bad. Second derivative. All right, so now things are going to start to get a little complicated. Remember that 1 over x was really x to what power? -1. So when I take this derivative, the -1 is going to come out. We're going to get x to the -2. That's really -1 over x squared, isn't it? And I'm going to go and I'm going to plug 2 into this, and I'm going to get what? -1/4. I'm going to do this until I'm very confident that I have a pattern established. I'm not confident yet that I have a pattern established. So third derivative. I'm going to take derivative of this now. So the negative and the negative hit, right? And you get positive. +2, x to the -3, which is 2 over x cubed. What would happen if you plug 2 into that? You get 2 over 8, right? Which of course is 1/4, right? But I'm going to keep it as 2 over 8 to try and, again, maintain visibility on the pattern. Like nothing canceled on this one, right? I didn't have a 2 on top and a 2 on bottom that canceled. This one I happened to have it happened to happen. Fourth derivative. So what happens now? -3 comes out and hits that 2, right? Yeah? So should I put -6? Maybe I should leave it as -2 times 3. Why would I do that?
Because factorial.
Because it looks like the next derivative, a 4 is going to go out there. And the next one, a 5 is going to go out there. So what I'm building up out there is what appears to be a factorial. Now this is -2 times 3 over x to the 4th. When I plug in 2, -2 times 3 over, what, 16? You want to do another one? One more? Fifth derivative. What? 2 times 3 times 4? Because it's negative and negative. So 2 times 3 times 4, x to the -5, which is 2 times 3 times 4 over x to the 5th power. Plugging in 2 times 3 times 4 over 32. Do you have enough to see the pattern? Yes.
Without knowing to do that, how far would you go?
As far as you need to make sure you're sure about the pattern. See, I think if you would have stopped here, you may have thought that just, look, the bottom just keeps going up. Like if you would have stopped there, you said, okay, yeah, and the next one's going to be 8, and 16, 30. What you would have never maybe seen is the factorial thing on the top happening. Maybe, I don't know, it depends on you. There's no rule of thumb like you have to go 5 derivatives. I mean, every problem is its own little thing. You got to just kind of go till you're comfortable. So let's take a look at these. Here they are, right? These are my numbers. All the bottoms, right? All the denominators are just powers of 2, aren't they? Except this one. That one does not fall into the pattern at all, does it? So what will I do with that? Well, I won't even care about it right now, okay? If there's only one that's not following the pattern, I'm not concerned. I can always just peel that off the front of the series, just leave it by itself. So this is 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So in terms of the derivative, when we take the first derivative, that determines the power on the 2, doesn't it? The second derivative is the power on the 2. The third derivative is the power on the 2. So we should have some connection between the derivative I'm taking and the power on the bottom, yes? What about the numerator? 2 times 3 times 4. Ignore the negative and positive for now. 2 times 3, 2, 1, 1. We said these look like factorials, right? Like this is 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. Good, that works. And then if this is 4 factorial, but it's happening at the 5th derivative, it's 1 less than the derivative, isn't it? So like if I'm on the 4th derivative, I only want to do the 3rd factorial. So n minus 1 is something that I'd be using for that. And then I have to look at the fact that it alternates. And again, I'm going to ignore the first one. And I'm just going to look at what? Positive, negative, positive, negative, positive, thinking negative next. We got all that? Now we have to put it together into a formula. Into the Taylor series, which is this. I'll keep all that over there. All right, the Taylor series should look like sum n equals 0 to infinity, c sub n, x minus a to the n, which is c sub 0, x minus a to the 0, plus c sub 1, x minus a to the 1, plus c sub 2, x minus a squared, c sub 3, x minus a cubed. That's just the general formula. And what I'm going to do now is come in and just replace all these pieces with what I have. What is c sub 0? It's natural log 2, right? right? Divided by what? Don't forget, look. So c sub n is the nth derivative at a over n factorial. Don't forget that n factorial. This number right here is the top piece. The factorial is always going to be on the bottom. So c sub 0 is the 0th derivative at 2, which is this, over 0 factorial. So natural log 2 over 0 factorial, x what? X minus 2 to the 0 power. Which of course that's going to be a 1, but I'm just showing you how I'm plugging in where I'm getting all the pieces. Can I go on? What's c sub 1 for us? It's this number, 1/2, right? Over 1/2 over 1 factorial, x minus 2 to the first power. What about the next one? Negative 1/4, right? I'm going to write it, though, like this. Negative, instead of 1/4, 1 over 2 squared, because that's where I'm picking up that power pattern. 1 over 2 squared, and then over what factorial? Where am I at? 2 factorial? X minus 2 to the second. What's the next one? C sub 3, which one was that? It was 1, 2, it's this one right here? It was 2 over 8, which I'm going to write as 2 over 2 cubed over 3 factorial, and then all that x minus 2 to the third. I'm running out of room. Next one. This right here. So it's going to be positive or negative? Negative. So I've got negative 2 times 3 over 16, which I'm writing as 2 to the 4th, over what factorial am I at here? 4. Does this look like a mess? And x minus 2 to the 4th. One more. Plus, because the next one would have been positive, right? 2 times 3 times 4 over 2 to the 5th over 5 factorial x minus 2 to the 5th plus dot, dot, dot. The numerator is a factorial, yes. That's exactly what I wanted to point out to you, because we talked about this when we saw the pattern. This right here is a factorial, isn't it? This right here is actually 4 factorial. This right here is 3 factorial. This right here is 2 factorial. This right here is 1 factorial, and this one right here is 0 factorial. And then this one right here, this didn't follow my pattern, so it's isolated by itself out here. I'm gonna try and come up with a formula for this right here, right now, with everything from here on. See if you can do it with me. All right, this right here, I'm going to rewrite as natural log 2, because that's what that turns into if I replace 0 and, all right, plus sum n equals 0 to infinity. And now let's start talking about this. It alternates. Positive, negative, positive, negative, positive, negative. So I need to start an alternating series. It needs to start with a positive number. So -1 to the n, because if n starts at 0, that should do it. Now let's start taking a look at all these pieces here. I've got a fraction on top, which is what? 0 factorial over 2 to the first power, right? So 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. Just n factorial. Right? Because look, if I start at 0, what's my first one going to be? Positive number, 0 factorial on the top, right? Over what? 2 to the n plus 1. Because look, you want 0 factorial, but you want 2 to the first power. Here you want 1 factorial, but you want 2 squared. Here 2 factorial, but you want 2 cubed. So this is over 2 to the n plus 1. But all of that is over what? 1 factorial, 2 factorial, 3 factorial, 4 factorial, so n plus 1 factorial. I know this looks like a disaster. I'm going to make this a little shorter up there like that. All of this times, right, I've taken care of all this crap that's happening out front. And then it's x minus 2 to what? I want my first one to be 1, right? So how about n plus 1? Almost done. Almost done. I can simplify those factorials because there's an n factorial and n plus 1. So how about we do this? Everyone hopefully understands that this is a fraction divided by a fraction. Fraction divided by a fraction, so I can flip reciprocal. So that's really n factorial over 2n plus 1 times n plus 1 factorial. That's what would happen if you flip that. And then using what we've done before, I peel off an n plus 1 on the bottom with the factorial and then cancel these factorials. So that would leave me with the following Taylor series. Natural log 2 plus sum n equals 0 to infinity. I still have the -1 to the n out there. I didn't touch that. But this stuff turns into 1 over 2 to the n plus 1 times n plus 1. And then I have x minus 2 to the n plus 1. This is the Taylor series for f of x equals natural log of x about a equals 2. Any questions? I think it's worth showing you one last thing. This will be the very last thing that we talk about this semester. Okay? And, well, let me do it, and then I'll ask you, does this seem like a problem you would want on the final, or would you want it more as a bonus? All right? So let me show it to you first. There's a background to this story. Have I shown y'all the Bad Professor video? Have y'all ever seen the Bad Professor video? Damn, I wonder if we have time.
We have about 20
Okay, you know what we can do?
Yeah, we have 25 minutes.
We have 25 minutes?
Yep.
Well, I have something to show you still, so, but I'll show you the motivation of this. So if we could get the lights, please. Yeah, let's go. Dark. Oh my gosh. I'm not showing you this because I'm searching YouTube right now, and my goodness, man. The things coming up when you type in worst teacher. There he is. All right, so let me see.
Hyperbolic this is 1x, and that is for 2 terms, that is for 4 terms, for 8, and the general solution.
It's only a minute long, so pay
Whatever.
attention, please.
You have the terms written. That is clear? Can you do such kind of drawings?
What?
Can you do it? If you have your homework, do some drawings. It is not asked for you, but do it. And send the drawings. Can you? You have some homework for the next time. Exactly of this kind. Do it. Do some drawing. Okay?
Hold on a second. That's not the one. Oh, here it is. Horrible teacher. All right, there we go.
Going on.
Okay.
It seems that you are not happy.
Okay, let me translate for everyone, okay?
Why not?
Do it, and if you do it manually, it doesn't work. It doesn't make any sense.
Okay, let's go further.
Okay, so the students go on to laugh and leave comments. The professor's telling them what? In order to do it, you multiply, right? And then the student asks, how do you do it? It can't be done. It doesn't work. and the professor completely blows them off, right? I don't necessarily agree with the professor's approach. However, it's just multiplication, and the student doesn't know how to do it, and the teacher thinks that he's kind of pulling his leg a little bit, like, okay, wait, you don't know how to do this? Like the teacher's confused that a student in that class wouldn't know how to do that operation. So what I'm about to do here right now is an example of that. And this is part of what's in this, at the end of this section. It's multiplication and division of power series. How do you take a power series and divide it or multiply it by something? All right? So you always have to be careful. Can get one more? You always have to be careful. You know, there's a reason why that guy looks like Albert Einstein. He is very brilliant. I don't know who he is, but I'm sure he's a brilliant mathematician. I assure you his mathematics up there is right because he's probably going off of his notes that he's written and they've already been proofed. The fact that the student can't follow him isn't his fault, especially if it's a topic. This is not a Cal 2 class. This is something else, differential equations or something further along. So this is a prerequisite topic that the student is asking him about, right? You understand? Okay. So what I'd like for us to do is I'd like for us to figure out, find the first, that says first, 3 terms of the power series for the function f of x equals 1 over sine x. Which would be the equivalent of me saying to find the first 3 terms of the power series for cosecant x, right? But so what we're going to do is try and convert this into a power series. And we're going to use the fact that we do know what the power series expansion of sine x is, right? The Maclaurin series. It's on our sheet. It is exactly what this would become 1 over. So what's the power series for sine? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 right? So what I have here is division, don't I? I have division. I have 1 divided by this infinite series, right? Okay. I'm going to look back up here at this guy's work. We're not, by the way, we're not doing the problem that they're doing right there, but I want you to see that if I back up this video where he points to the board right there, I want everyone to see, get over here, 1, boy, you can't see anything down here, 1 divided by an infinite series. Do you see it? That's what the student couldn't do. Because he goes from this line to this line, and the student can't follow how that division is possible. And if you look on my YouTube channel, on my playlist, I actually work through that problem and show how it's done because I thought it was worth working it out, you know? Just look up a horrible teacher on my channel and you'll see me work it out. But okay. So how do we divide this? How do you divide 1 by this? Well, how do you divide old school division, right? Like, what's 13 divided by 4? Well, you did this, right? That's what you did. And that's what we're going to do now. We're going to do long division on this. And on the inside of the division is the 1. Right? And on the outside is the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. But I can't keep going, right? That thing is infinite. And then we're going to do kind of like we used to do when we had long division here and we had a polynomial and like a polynomial in there. We would try and turn this, usually it was the highest power out here. We try and turn it into this. But because our powers get bigger, I'm going to actually start here. How could I turn x into 1? What would I have to multiply x by to turn it into 1? 1 over x, right? If I multiply x by 1 over x, wouldn't I get 1? And now what we do is we pass the 1 over x through every single one of these. All right? And we write those down below here, and then we subtract. Do y'all remember this with long division? Okay, so let's do it. 1 over x times x gives you 1. 1 over x times this. What is the effect of hitting this with the 1 over x? It brings the power down. The numbers all stay the same. So I'll get negative x squared over 3 factorial. What would the next one be? Plus x to the 4th over 5 factorial. Next one, minus x to the 6th over 6 factorial. And that keeps 7 over 7 factorial. Plus dot dot, and it keeps going, right? And then you're supposed to come through and change the signs. So subtract that row, so that minus 1, or that 1 becomes minus 1, this becomes a plus, this becomes a minus, that becomes a plus, right? Everything changes. And then you add straight down, don't you? So when we add straight down, the 1's cancel, which is what we wanted. And now I go here and here, add down, we get x squared over 3 factorial. Here, negative x to the 4th over 5 factorial. And then plus x to the 6th over 7 factorial. And we go again. What do you have to multiply x by to turn it in to x squared over 3 factorial? X over 3 factorial, right? I multiply this x times x over 3 factorial, I'll turn it into this. So my next term is, keep on switching my blues. X over 3 factorial. And that, if I multiply this times this, I should get this, right? Things are going to start to get kind of ugly here, if they haven't already. Okay? So far, I have the first 2 terms. Do you see I have the first 2 terms? This, the division that we were trying to do, 1 over sine x, that was 1 divided by an infinite series. When I do the division, I have the first 2 terms so far. So I'm just going to have to do this one more time after I come through here. So what is x over 3 factorial times x? That gave me the x squared over 3 factorial, right? This is where things get pretty crappy. What's x over 3 factorial times negative x cubed over 3 factorial? It's negative x to the 4th over 3 factorial times 3 factorial. Just leave it like that. 3 factorial times 3 factorial. We'll resolve this in a second, all right? Y'all see what I'm doing? One more multiplication. Let's do x over 3 factorial times x to the 5th over 5 factorial. What would that give me? X to the 6th over 3 factorial times 5 factorial. And I could keep going, but I'm not going to. And then I come through and change the signs and add down. This becomes minus This becomes plus. This becomes minus. What's the only one of these things I'm worried about? This one's going to cancel, right? Just this one. Why?
It tells you what.
That's right. Whatever this turns out to be, that's what I need to multiply x to get, right? So if I can just get this one, I'll know what my next piece up here is. So we got to put these two together. So we better go look at those over here. I'm taking negative x to the fourth over 5 factorial, and I'm adding or subtracting? Adding what? X to the fourth over 3 factorial, 3 factorial. What do those both have in common? X to the fourth. Pop the x to the fourth out then. And I'll put it at the back. I'll have negative 1 over 5 factorial plus 1 over 3 factorial, 3 factorial. Isn't that what it is? I mean, I could go figure out what this number is, but I'm not going to. I'm going to leave it just like that. So that's what belongs right here, right? So what do I have to multiply x by to get this? X to the third, but in front of it, what? That whole thing. Negative 1 over 5 factorial plus 1 over 3 factorial, 3 factorial. So if I take that, I multiply it times x, and then bring it down, and then subtract, it'll go away. You all follow that? These are the first 3 terms. Of course, there's more. Good thing I didn't ask for the first 10, right? Questions? Yes?
Is that going to be on the sign?
Well, now let me ask you. Does this seem like a problem that you would like to be able to do, or a problem that you would want to only do as a bonus? Just find the first term? Find the first term. I like that. That's a good idea. All right, well. So no, y'all don't want this? No. Okay. Well, just remember, if you're ever sitting in a class and you're getting mad at the professor because you don't know how to do it, don't come back to me. All right? Remember, you said you didn't want to get into this. So
Do we use this in calculus?
you won't use that in Cal 3. No. Differential equations. Series come up again. They do come up again. But in Cal 3, they don't. All right, so I think we're done. We have 7 minutes. Let's talk about the final. I'm gonna send you out a copy of last semester's final, which was very heavy in chapter 8. So imagine now, this is what I was telling some other students. Imagine that I give you a function and I ask you to find its power series, like from the 8.6, something like 1 over 3 plus x, and I say find the power series for that. Or even worse, it was the one where it was squared and you had to do like a derivative or integrate or something to make that happen. So find the power series. So you go through all the work, you find the power series. I ask you to find the interval of convergence. So you have to do a ratio test, check the endpoints. If I ask you just that one problem, there's like 3 or 4 sections worth of material in that one problem. So I'm imagining it'll be a rather short final, but to focus most of your attention on chapter 8. Right? I don't know. I mean, I haven't written the final, so I can't tell you. So. It's on Thursday at 12:30. Thursday at 12:30. I'm going to send an email out tomorrow morning that will have what days and times I will be here next week, because office hours are never normal the week of finals because I'm giving finals. And the makeup lecture thing, bonus thing that I've been wanting to offer you. Had y'all thought about Friday, tomorrow?
How many bonus points exactly?
Yeah. I don't know. I'm thinking maybe doing it after the final. Like not immediately after the final. Maybe like Friday after the final type thing. I don't know. I'd like to see how you feel after the final, and if you feel like, oh my gosh, I'm going to need every bonus point I can get, then
It should be on a
you
day
go.
normally classes, because if people have other obligations already, they can't.
I know, but I can't do it during those other times because other finals will be taking place. It's hard to do. It's hard to do any lecture outside of this. It's hard to do.
I think next Friday
So,
would work
yeah.
the best.
And
We got a lot of other
yeah, some people work though, so. I think right now everyone should just focus on getting ready for the final. I think that's the most important thing. Look, I've posted all the solutions to all them. I've been really working hard to get all the problems in the homework done so that they're on video for you. I hope you're taking advantage of that. I know that I can see how many people have watched my homework solutions, and you know, there's not many that look at me doing the homework, which is fine, but especially for this stuff, all the little details in there, I advise you to watch it, all right? Now for 8-7, what I would look at, I give you homework last time or no?
Yes.
Did? Well, I didn't for 8-7. I did, no, did I? I did 8-6, right? For 8-7, 5 through 17 is what I've done so far. You should at least do 5 through 17. And you said you didn't really want to mess around with adding or dividing, and so we'll just say 5 through 17. I'll kind of trim it back a little bit. Pardon?
Would you still do some examples of the last problem?
For bonus, you mean like a yeah, I'll put one on as multiplication division. And if you want to look at those in the book, the multiplication, division, and power series are 55 through 58. That's multiplication and division of power series. You're allowed to use this on the final. You're allowed to use the convergence tests. All those convergence tests. You're allowed to use the standard, the packet thing, whatever. Okay, that you're allowed. There is one problem I have to put on the final. The math department requires me to. So make sure you can do a volume of a solid of revolution. Just at least look at that again, like how you find a volume, rotating regions. That'll be on the final, not by choice. All right, well, I guess that's it, right? Adios. See you on Thursday.
Sir, that's Washington.